Okay, so we're surrounded by powerful electric motors. They're in everything from industrial pumps to the escalators you ride every day. But have you ever stopped to think about how they actually get going? It's not as simple as just flipping a switch. In this explainer, we're going to pull back the curtain on the surprisingly violent physics of starting a motor and find out why they need these special devices just to turn on.
So let's get right to the core question here. Why can't we just hook up a giant motor directly to the power grid and let it rip? I mean, we do it with our blenders and vacuums all the time. What makes a big industrial motor so different that it needs this whole separate piece of gear called a starter?
And this, right here, is the perfect analogy. Seriously, imagine you're thirsty, and you try to get a drink by cranking a fire hydrant valve all the way open in a split second. The raw, uncontrolled power of that water would be, well, destructive. Starting a big electric motor is the electrical version of that exact same thing. It is a sudden, massive, and potentially really damaging blast of energy. Now, there's a technical name for this electrical flood. It's called inrush current. You'll also hear it called locked rotor current, which makes sense because it's the current the motor pulls when its rotor is still stationary, or, locked. The instant you hit it with full power, the motor tries to gulp down this colossal amount of current, way more than it needs to just run normal.
And this is no joke. The damage from that surge can be huge. First, all that current creates a ton of heat, enough to literally melt the delicate copper windings inside the motor itself. Second, it's such a huge draw that it can actually cause the voltage in the whole building to sag. Lights flicker, other equipment gets disrupted, and finally, it's a huge mechanical shock, a violent jolt of torque that can slam gears and break the very machine the motor is supposed to be running.
So how in the world do we fix this? How do we stop this electrical fire hydrant from blowing the whole system apart? Well, this is where the hero of our story enters the picture. The motor starter. The best way to think of it is as an intelligent valve, or maybe an electrical shock absorber.
So to put it really simply, a motor starter is way more than just an on-off switch. Its whole job is to intelligently manage and control that initial blast of power. It's there to protect the three most important parts of the system: the motor from burning out, the machinery from that mechanical shock, and the electrical grid from a disruptive voltage dip.
Okay, so now that we get why we need a starter, let's dive into how they actually work. For the most common type of industrial motor out there, the AC induction motor, engineers have a whole toolkit of methods. We're going to take a look at the three big ones. First up is the most basic no-frills method. It's called direct online, or just DOL starting. And this is pretty much our baseline. It's basically a super heavy-duty switch that does exactly what we just said was dangerous. It connects the motor straight to the full power supply. It is the brute force approach. But hey, for smaller motors where that surge isn't catastrophic, it's simple and it's cheap.
Now, let's get a little more clever. Meet star delta starting. This one uses a really neat electrical trick. The motor's internal wiring gets connected in what's called a star configuration first, which lowers the voltage the motor sees. Then, after a few seconds, once the motor's got some momentum, a timer clicks over and switches the connections to a delta configuration, which applies the full voltage. It's a much gentler two-step start.
And this slide just lays out the trade-off perfectly. I mean, look at this data from the ABB motor guide. Starting in that star configuration cuts the starting current all the way down to about 30% of the direct online method. That is a massive improvement. But, and this is a big but, look at the starting torque. That's the initial turning power. It plummets to just 25%.
So what does this actually mean? It means star delta gives you a much kinder electrical start, but it absolutely comes at a cost. You give up a huge amount of that initial oomph, that turning force. That makes it fantastic for things like fans or pumps that are pretty easy to get spinning, but it's probably not going to work for, say, a heavy conveyor belt that needs a ton of muscle right from the get-go.
And this brings us to the modern solution, the soft starter. Now, this isn't some clunky mechanical switch. This is a smart electronic device packed with power electronics. Instead of a clunky two-step process, it smoothly and gradually ramps up the voltage to the motor. The result is a perfect, stepless, buttery smooth acceleration.
This chart just gives us the perfect visual. Direct online is that giant instant spike in both current and torque. Bam! Star delta is that big step down. A huge reduction for sure, but the soft starter? It's that beautiful, smooth ramp. It is by far the most controlled, gentle, and sophisticated way to start an AC motor. Okay, so we've been talking all about AC motors, but what about their cousins, DC motors? Well, it turns out they have their own totally unique reason for needing a starter. And it all comes down to a really fascinating bit of physics.
So we need to talk about a concept called back electromotive force, or back EMF for short. You see, as a DC motor spins, the wires moving through its magnetic field actually start to act like a little generator. They create their own voltage. And this voltage pushes back against the power supply. It's like the motor's own built-in defense mechanism that naturally chokes back the current once it's up to speed.
So you can probably see the problem here. When the motor is at a dead stop, it's not spinning. And if it's not spinning, it's not generating any of that protective back EMF. With nothing pushing back, the supply voltage can just force a massive, unrestricted flood of current through the windings, which can be just as damaging as the inrush current we saw in AC motors.
So how do you solve this? Well, DC starters have a few different strategies. The classic way is to put these big resistors in the circuit to act like temporary speed bumps for the current. As the motor picks up speed and its own back EMF starts doing the job, those resistors are taken out of the circuit one by one. More modern methods use smart electronics to either control the voltage precisely or to chop it up into tiny little pulses, a technique called pulse width modulation, to gently ease the motor into motion.
So as we've seen, motor starting has come a long way. We've really gone from these simple, clunky, heavy-duty switches to highly intelligent electronic controllers that do way more than just start and stop.
This timeline really sums it all up, doesn't it? In the past, it was all about these robust but kind of crude mechanical solutions like DOL and star delta. Today, electronic soft starters are super common, giving us way more finesse and control. But the future? The future is all about total integrated control.
And that brings us to what is really the pinnacle of motor control. This quote from the ABB Motor Guide hints at something that goes way beyond just starting. It's talking about adjusting the speed while the motor is already running.
This device is the Variable Speed Drive, or VSD, and it's the ultimate controller. A VSD gives you an incredibly gentle start, sure, but its real magic is controlling the motor's speed with pinpoint precision through its entire operation. By matching the speed exactly to what the load needs, it can save just enormous amounts of energy. And on top of all that, it can also bring the motor to a smooth, controlled stop. It's the whole package. Which kind of leaves us with a final big question. As these incredible devices like VSDs become more common, offering starting, stopping, and complete speed control all in one box, are we watching the end of the traditional separate motor starter? Is this simple, hard-working device destined to become a relic of a less sophisticated electrical age? It's definitely something to think about.
Thanks so much for diving into this with me. I'll see you in the next one.
Let's study more and like, share, and subscribe for such more content. And comment something you want to learn.